Good afternoon, everybody. Welcome to the latest in the Veramed webinar series. Today we have James Diserens talking to us about Surviving Your Statistician, a Programmer's Guide to Survival Analysis. James originally graduated with a BSc in Physics, and he started work as a SAS programmer in 2014, working on Phase 1 clinical trials, subsequently joining Veramed as a statistical programmer to continue developing his technical and statistical skills. So without any further ado, I will pass you straight over to James. Thank you, James.
Thanks. Yeah, so my background was physics. It involved a lot of maths, and that included quite a lot of statistics. However, it didn't cover some of the more niche methods that might be used within clinical trials. So when I came to Veramed, I had very little experience of survival analysis, which is something that I ended up working on quite a lot. So I worked with some of the senior statisticians to learn more about and to understand better the outputs that I was going to be producing. So today I want to cover the main concepts of survival analysis and how they're likely to be used within clinical trials. I think it's important because it helps with a programmer to be able to recognize exactly what's going on when they're producing outputs rather than just building to a spec. So to do that, I'm going to talk about two main methods. First of all, the Kaplan Meier. I want to look at how censoring can be used within Kaplan Meier, the PROC life test in SAS, and an example of how you'd use this within a clinical trial. Then I want to cover the Cox proportional hazard method, look at hazard ratios, PROC pH reg within SAS, and the use of covariates for improving the analysis. So survival analysis is the method used to analyze time to event data. The name suggests death and how subjects might survive through a study, but it can also cover other events, stuff like the time to a heart attack, the time to relapse of cancer, or away from clinical trials, something like the time to failure of components or devices in something like engineering. These endpoints need to be a clearly defined, distinct point where the subject goes from one binary state to another. So there's no gradual phase, it's has the event occurred, yes or no. The advantage of survival analysis is you can use censoring. This enables data from subjects that perhaps might be incomplete, withdrew early, or did not experience a target event while being recorded. But survival analysis can also accommodate for the positive skew that often occurs. So in clinical trials, it's often the case that a large number of events are quite likely to occur early in the study, and then the rate slows down later on. First, let's look at Kaplan Meier. So Kaplan Meier estimate is quite widely used to show survival over time. It's usually calculated as the product of the event rate over a small series of steps. So the survival estimate is equal to the product of that equation there, where you calculate the event rate as the number of subjects remaining over the number of subjects at the start. And this is usually represented using a Kaplan Meier plot, where you use a series of steps which cover each of those small time intervals. And this will show the estimated survival over time. So now I want to talk through an example, a pretty basic example of how you might use Kaplan Meier. So if we think of 10 subjects that come in and are reviewed once daily over a period of, say, 10 days, And if their events are recorded on day 1, 4, 8, 10, and say 2 events on day 5, then I'm going to show how you might record this. So at the top here, I've got what is known as a life table. This records the number of subjects at each time point, and then calculated the survival estimate. And at the bottom, an example of how you build out the Kaplan Meier plot. So if an event occurred on day 1, you'd have 10 subjects at the start, 9 at the end, so 9 out of 10 have survived. And on the plot you can see the line goes across at 1 until you hit day 1, and then steps down to 0.9. So the survival estimate from day 1 until the next event is then 0.9, and that's plotted as a horizontal line on the graph. Then if another subject experienced an event on day 4, you'd step down again. Here, the survival probability from day 1 to day 4 is calculated as the number of subjects remaining divided by the number of subjects at the start, which is 0.89. The survival estimate is then that multiplied by the previous survival estimate, which gives us 0.8, where 8 subjects are remaining out of 10. This is pretty obvious stuff. Again, the next step, 2 subjects withdrawing on day 5, also 2 subjects experiencing the event. So you step down to 0.6 and then go across to day 8 when the next events occur, and so on to day 10. So far that's pretty straightforward stuff, fairly simple, but for survival analysis the advantage comes when we start to talk about censoring. So the complete follow-up of subjects is not always possible, and if you have this incomplete data, it can be frustrating to have to withdraw the subject, take out anyone who hasn't experienced the event, and it can also introduce bias into the study. So we use what's known as censoring, and in clinical trials this is usually right censoring. So this would be where you know the start time for the subjects, but by the time the subject withdrew, you do not see them experience the event. And there could be several reasons why this could happen. You could have the study ending before the subject experienced the event, in which case you wouldn't know the time until the event occurred, but it would also be incorrect to say that the subject would never experience the event. The subject could withdraw early or be lost to follow-up during the study, or they could have what's known as a competing event, which is another event that stops the event you're interested in from happening. Now, it's necessary to assume that once a subject has been censored, they have the same risk of an event of all those subjects that can be followed up. Now, this would not necessarily be true, as often those subjects that withdraw from a study, the reason why they withdraw could affect how quickly the event would occur. And when you're displaying this on a Kaplan Meier, you'd usually mark a cross where each subject is censored. So if we look at the same example now with 10 subjects, but here where one subject withdraws on day 3 and one on day 7. The plot is built the same and the life table is the same up until day 1. And then as we come across horizontally here, you get to day 3, you see there's marks across here, that's where a subject is censored. The line then continues across horizontally up until day 4, where the next event occurs, and we recalculate the survival estimate. Now, because we've had this one subject withdraw and they become censored, we exclude them from the calculation of the survival probability here. So now we have 7 out of 8 subjects remaining and a survival probability of 0.875. And this is where we change from the previous example, and the survival estimate is now calculated and is actually slightly lower. It's 0.788 instead of 0.8. You can see on the plot it's a slightly larger step here. And then we will move on to day 5, where 2 events occur. You're now having 5 out of the 7 subjects that remained. And again, you have a slightly larger step down here because you're calculating the event rate out of a smaller sample size. So we continue on and go through day 7. It's marked again where there's a censoring, and then recalculated on day 8. So you can see now this is much lower at 0.422. And we go through the final step, and we get a survival estimate over the 10 days that finishes at 0.28 as compared to 0.4 without censoring. So you can see in this small sample there's quite a big difference when you include censoring, in that although we had the same number of events occurring, you're now factoring in the subjects where you don't know the results, and as a result we get a lower survival estimate. Now let's have a look at how you do this using SAS. Using an example dataset input as data EX1 into SAS proc life test, and an output table of KM1 here, so that would be the tables like we produced by hand above. And the plots option tells us to produce a survival plot. We put plots equals S. Time would normally be recorded in the AVAL variable. So we cross that in the time statement with the censoring variable, where 1 states that the subjects have been censored and 0 would suggest that they've reached the event. You can see from the output here it produces the same steps. Got the censoring marks at day 3 and day 7, and resulting in a survival probability over 10 days, 0.281. So now we build it up to an example of a dummy clinical trial. So we said we had 8,000 subjects either on a placebo or a treatment over the course of 3 years. And we look at the primary endpoint being death. So there's 3 possibilities of what could happen to subjects here. The subjects could either have the event, they could die within the 3 years, they could survive for the duration of the whole study. So at the end of the 3 years, they're followed up, still alive, they'd be censored after 3 years. Or they could withdraw from the study and they would be censored at the point that they withdrew, which would be less than 3 years. Now, using the CDIS standards for clinical trials, this kind of data will be stored in the adam.adtte dataset. I've shown a quick screenshot of what that would look like and the important variables that you'd have. So you've got the param and the param code, which will just identify what the event of interest is, in this case, time to death. AVAL would contain the number of days until the event occurred. And the CNSR says whether or not censoring occurred or the event occurred. So in this example, 0 would mean the event occurred and 1 would be censoring. You can also have larger numbers. You have 2, 3 would be different types of censoring from the right censoring that we used. Again, put this into the SAS procedure, proc life tests, and now we've added a strata statement to split the results by the treatment groups. So this is the output we get from SAS. So you see, it's quite hard to see exactly what's going on with each line here. So we need to improve this. Unfortunately, proc live test isn't the best for customizing the output. So instead, I'm going to use proc sgplot combined with the output live tables. So at the top here, in this specific bit of code, I've used the ODS output product limit estimates. And this will just produce a live table that matches the graph that would be produced. You then perform the proc live test in the same way as we have before. And if you combine the product limit estimates output and the outside there, you will have the live table combined with the confidence intervals that you might want to plot on a graph. So in the sgplot section, I have plotted a series plot which would show the Kaplan Meier lines, a scatter plot that would add confidence intervals, and typically you wouldn't want confidence intervals at every time point. So processing this data, I've selected only every year. And then I've edited the axis to focus in on the relevant area of the graph. So this is what the output would look like. As you see, we're looking between the 0.7 and 1 regions of the survival function and have confidence intervals applied at 1, 2 and 3 years. We've also added a risk table at the bottom, so you can see the number of subjects who are at risk at each point in the trial. So for this study, we're looking at 4,000 subjects in each group, which reduces down to about 1,500 at the end. And that gives you an idea of how many subjects might either experience the event or have been censored over the course of time. So what does this plot show us? What we can see is that approximately 75% of the placebo subjects survived over 3 years, in comparison that approximately 90% of the treatment subjects survived 3 years. Now you can either show this as a survival plot going down, as we have above, or in some trials you might want to look at actually the number of subjects experiencing the event, in which case you'd start with time to event 0 and go up, showing the number experiencing the events over the 3 years. You can also compare groups by looking at median survival time, which would suggest the time taken for half the subjects to experience the event. Unfortunately, in this example, we never get below 50%, so can't show that. The results here don't necessarily mean that death is less likely to occur overall in that treatment group. What it does say is that there's a longer time to death in that treatment group. Now this is important because in some studies you can have a group that might experience a very quick rate early on in the study and so be lower early on, but then the rate would slow down massively and the lines might cross back over. So you can't say for certain that this hasn't occurred after 5, 10, 20 years. So it needs to be a longer time to death. Now, as I mentioned earlier, here we've assumed that censored subjects have the same probability of survival as those that continue in the trial, which is an assumption you have to make, but it's not known for certain. Withdrawn subjects, as I said, might have a reason that makes the event more likely to occur that might reflect why they've withdrawn. So the more frequent follow-up of subjects will increase the estimate. What that means is that if you have a smaller gap in time for each step, you're going to be more accurate on what you're estimating the survival at each individual time. As we saw from the risk table, if censoring is occurring a lot, you'll have a smaller sample size at time points later on in the study. So therefore, you've got greater precision in the Kaplan Meier graph, the left-hand side, than you do on the right. So Kaplan Meiers are very useful for comparing across, say, treatment, but they're limited because they can only factor in a single predictor. So we might want to use Cox proportional hazards because they can factor in a second predictor or a third or fourth, as many as you need. So these would be covariates, so another variable of interest that might be affecting the outcome of the time to event data. So the Cox proportional hazard produces what's known as a hazard. This is the instantaneous risk of the event occurring in a given time. And to compare across groups, we use what's known as a hazard ratio, which is simply the ratio for hazards between these two groups. So the hazard ratio is the value that we're going to look at. So here you can see what different values might mean. We have 0.5 hazard ratio. This would say that half as many subjects in a treatment group experience event compared to control group. Hazard ratio of 1, the rates are the same. And hazard ratio 2, twice as many subjects experiencing the event. We also look at what's known as the reduction in risk, and this is calculated simply 1 minus the hazard ratio. And normally this is displayed in a percentage. So if we look at this now in SAS with proc pH reg, and we're going to perform this on the same example as before. So here we use the class statement, as you might do in other forms of modelling. And this is just used to define the categorical variables. So something like treatment, where you either have placebo or treatment. And therefore we put the reference in that we want to compare treatment against placebo. So ref equals placebo. And then we want to build our model. So here we want to compare time to event. So that's the eval variable from ADTTE. And then we add in the censoring variable to say, has censoring occurred or has the event occurred? And the groups that we want to compare, treatment. The risk limit statement here at the end just gives us the confidence intervals on our output. So what do the results look like? Here we've got a hazard ratio of 0.441, which suggests that less than half of the subjects in the treatment group compared to placebo are experiencing the event. So we've got the 95% confidence intervals here, and the important thing to look for here is if those cross the value of 1. They cross the value of 1, it seems to suggest that this is not a significant result. And you can also check that from the p-value. So our p-value here is very low, so we can assume that this is statistically significant. If you convert that into the reduction of risk, it suggests that we've got a 50% reduction in risk of dying in this time. So what we want to look at with the Cox proportional hazard method is the covariates. As I said, these are variables that could also be associated with the outcome of interest. By including these, we can improve the estimate of treatment effect compared to what we might get from the Kaplan Meier or our previous results. So in our example that I've talked about, there were 2 covariates, age and sex. Data like this that might be a randomized clinical trial, though, you wouldn't expect to see any change with these. If it's randomized across, you should have a fairly equal distribution of those. So to put this into proc pH reg, we have sex added to the class because it's a categorical variable, and then simply add your covariates after treatment, so sex and age in there. Now, as you can see on the results here, the hazard ratio very similar to before, and the reduction risk of death is still at 56%, which is what we would expect to see. Okay, thank you. I think we have time for some questions now.